to this lesson. I'm teacher Agnes, and today we are going to be discussing how to measure pressure, or which instruments are used to measure pressure. So we are going to start by discussing how to measure pressure of a gas. And to get started, we are going to review these two apparatus here. So to begin with, we have a U-tube, okay? A U-tube is just a tube that is U in shape. And then we have a U-tube manometer. So a manometer is an instrument that is used to determine the pressure of a gas. Now, if you look at the U-tube, we have a liquid inside it, and you can see that the level of the liquid in both sides is at the same level. The reason why the level of the liquid is at the same level in both sides is because both sides, which are open, are experiencing the same amount of atmospheric pressure. So if you looking at this U-tube, if you are to blow if you are to blow on one side, there's a chance that the level of water on the other side is going to go up as the level of water in the side that you have blown goes down. Why is that the case? Because if you blow, you introduce a new pressure that was not there. And since you have only introduced it on one side, the pressure is going to be more and the liquid is going to be pushed downwards, and then it is going to go up on the other side to balance the pressure that you have introduced. So the more you blow, the more the level of the liquid will go up on the other side. Now that is a principle that we use when it comes to a U-tube manometer, because a U-tube manometer is also U in shape. So what happens is that in a U-tube manometer, like you can see, on one side there is a gas supply, okay? There's a gas supply, and this gas is supplied into the U-tube manometer. When that happens, the level of the liquid on the other side goes up. So the change in the height of the liquid translates to a certain amount of pressure, because remember, pressure in a liquid depends on the height of the liquid and the density of the liquid. So when this liquid on this side has its level go up, then it means there is a new pressure that is represented, or that is as a result of the new height of the liquid, and that pressure is the one that is equivalent to the pressure of the gas. Now, for us to be able to understand this better, we are going to do several questions so that we see how we can apply or how we can determine the pressure of a gas using a U-tube manometer. In this question, we have a U-tube, and inside the U-tube we have a gas that is trapped at the top here, and then we have mercury, and then you can notice that in the U-tube one side is open and another side is closed. So the side that is open, we have atmospheric pressure getting in and acting on this mercury at this side, and then on the side that is closed, we do not have atmospheric pressure acting on the mercury, but we have the pressure due to the gas acting on the mercury. So we have been provided with the atmospheric pressure, which is 100,000 pascals, the height of the mercury, which is 2 millimeters, the density of mercury. Remember, we said that Hg, capital H, small g, is a symbol used to represent mercury. So when you see Hg, you know we are talking about mercury. So this is the density of mercury, which is 13,600 kilograms per meters cubed. Then we have the gravitational force as 10 newtons per kilogram, and we are required to determine the pressure of the gas. Now, when you look at this U-tube, you realize that the level of mercury is not the same in both sides. So the level of mercury inside A is higher than inside B, meaning that the pressure acting on this side is pushing the mercury to go higher on this side. But what you have to note is that at any two levels, the pressure is the same, okay? At any two levels, levels such as A and B, the pressure acting at A is the same as the pressure acting at B. So now we can have it that pressure at A is equal to pressure at B, okay? Pressure at A is equal to pressure at B. Then now the next question you ask yourself is, what is causing pressure at A? What is exerting pressure at A? So for you to know that, you just need to check what is above A. So above A, we have the mercury, then we have the gas. So at A, we have pressure of the gas and pressure due to the height of this mercury. How do we calculate pressure due to the height of a liquid? We have height times density times gravitational force. And this is equal to the pressure being exerted at B. So above B, we don't have mercury, we don't have any other gas, we just have atmospheric pressure. So atmospheric pressure is the one that is exerting pressure at B. This is how you come up with your formula. For every of these questions, you will realize that the formula is different. But the trick in getting the correct formula is by first asking yourself, which two levels have the same amount of pressure? They should be on the same level on either sides. Then ask yourself, what is causing pressure on one side? And then equate to what is causing pressure on the other side. Now, we do not know the value of the pressure of the gas. That is what we are looking for. Now, the height of mercury is 2 millimeters. Remember, you cannot use millimeters in this equation because that is not the SI unit of length or of height. So we have to convert millimeters into meters. So since we have done this before, we learned that converting millimeters to meters, you have to divide by 1,000. Then we multiply by the density of mercury, which is 13,600, times the gravitational force, which is 10. And this will be equal to the atmospheric pressure, which is given as 100,000. Okay? So now we can simplify our equation. So pressure of the gas remains plus, these two zeros cancel out here, this one cancels out with this one. So now we have 2 times 136, which is equal to 272. And this is equal to 100,000. So since we are interested in the pressure of the gas, okay, the pressure of the gas will be equal to, we take 272 the other side, and it becomes subtraction. So this is 100,000 minus 272. So the atmospheric pressure now minus the pressure due to the height of mercury. So if we subtract these two, then we will be able to get 99,728 pascals. Okay? So this value that you have gotten here represents the pressure of the gas. That is why these two levels are balancing, because the pressure here, atmospheric pressure, is equal to the pressure due to mercury, 272, plus the pressure of the gas, 99,728, which is equal to the 100,000 pascals on the other side. Now let us look at another question that has been, framed differently. Now in this question, we still will be required to determine the pressure of the gas that is trapped in this region. But you notice that it is slightly different from the one that we have done. Now in this question, just like in the previous one, we are going to begin by identifying the two levels that are the same or that have equal amounts of pressure. So we can call this A and this one B. So like you can see, level A and level B have the same amount of pressure. So pressure at A will be equal to pressure at B. So what we are going to do now is to identify what is causing pressure at A, what is exerting pressure at A. Above A, we only have the gas. So it means that pressure at A is as a result of the pressure due to the gas. So pressure of the gas. Now since we don't have anything else above A, and since the tube is closed here, then we cannot have atmospheric pressure acting at A. We can only have atmospheric pressure acting where the tube is open. So pressure of the gas will be equal to pressure at B, which is as a result of the height of mercury, okay? So height times density times gravitational force plus. Now since the tube is open on that side, then it means that we have atmospheric pressure acting here. So we are also going to add atmospheric pressure on this side. Now do you notice that this formula is different from the one that we formulated in the previous lesson? That means that there is no definite formula that you can use to determine the pressure of the gas. You just have to be guided by the question. Now pressure of the gas will be equal to, since we know the height of mercury, which is 40 centimeters, can we use 40 centimeters as it is? No. We will have to convert the centimeters into meters. Do you remember how to convert centimeters into meters? You divide by 100. Then we multiply by the density of mercury, which is given as 13,600 times the gravitational force, which is 10. And then we add to the atmospheric pressure, which is given as 100,000 pascals. Now working out here, we have the 2 zeros cancel out, and then 40 times 136 times 10 will be equal to 54,400, and then we add to 100,000, and this will be equal to 154,400 pascals, and this will be the pressure of the gas that is trapped on this side of the manometer. So let us look at one more different formulation of the question. Now this is yet another formulation of a question that requires us to determine the pressure of the gas that is trapped on one side of the manometer. So like you can see, we have two liquids in this case, which means the two liquids have different densities. So on one side we have water that has rose to a height of 20 centimeters above B. Then on this side we have mercury that has rose to a height of 40 centimeters above A. Then inside here we have the gas. And then since this side is open, then it means we have atmospheric pressure acting on that one side of the tube. We have been given the density of water as 1,000 kilogram per meters cubed. The atmospheric pressure is 100,000 pascals. And the density of mercury as 13,600 kilogram per meters cubed. The gravitational force as 10 newtons per kilograms, and of course we are looking for the pressure of the gas. So in this question we are still going to follow the same format. They may be structured differently, but the way of coming up with the formula is the same. So we are going to begin by identifying the levels where the pressure is the same. So here we have A and then we have B. So region A and region B have the same amount of pressure because they are on the same level. So pressure at A is equal to pressure at B. Now the next question is to ask yourself, what is causing pressure at A? So to know that, you have to check what is above A. So above A, we have the gas, then we have mercury. So pressure of the gas plus pressure due to the height of mercury. And pressure due to the height of a liquid is calculated by height times density times gravitational force. Now you can call this height 1 and density 1. Now this will be equal to the pressure at B. So what is above B that is causing pressure at B? So 1, we have the atmospheric pressure. Then we have pressure due to the height of the water. So again, H rho G. So we can have this as H2 rho 2. So we do not know the pressure of the gas yet. Plus, the height of mercury is 40 centimeters. Again, you cannot use 40 centimeters as it is in the equation. You have to convert it to which units? To meters. So 40 divided by 100 times the density of mercury, which is 13,600 times 10. Now in this question you have to be very careful because we have two different heights and two different densities. So you have to make sure that you are using the correct density with the correct height. Okay? Now this will be equal to the atmospheric pressure, which is equal to 100,000 plus pressure due to the height of the water. So the height of water is 20 centimeters. So we divide by 100 to convert it to meters times the density, which is 1,000, then times the value of the gravitational pull, which is 10. So now if we work out this, we will get pressure of the gas, okay, plus, so 40 times 136 times 10 will be equal to 54,400, and this will be equal to 100,000 plus, so if we work this out, we will have 20 times 10 times 10, which is equal to 2,000. So now, pressure of the gas plus 54,400 will be equal to the sum of the two, which is 102,000. So now, taking 54,400 to the other side, we will have the pressure of the gas being equal to 102,000 minus 54,400, and this will be equal to 47,600 pascals, and that will be the pressure of the gas. So I hope you have noticed that each of these questions is formulated differently, but the way you argue out is the same. However, the formula you come up with is different for every question. Now, a YouTube can also be used to compare the pressure of liquids that have different densities. So now we are going to do some questions that do not have a gas trapped in here, but have different liquids in the YouTube, and find out how to go about that. Now in this question, you realize that these are difference, or rather they are differences. So in this type of question, both sides of the manometer are open. Then we also don't have a gas that is trapped inside on one side. So in this question, you're not going to be concentrating on looking for the pressure of the gas because there's no gas that has been trapped. Now, if you look at both of these sides, we have atmospheric pressure acting on this side. We also have atmospheric pressure acting on the other side. So if you were to input them in the question, such that on one side of the equal sign you have atmospheric pressure, and on the other side you also have atmospheric pressure. You realize that when you bring atmospheric pressure from one side to the other, then the two will subtract and give you 0. So when both sides of the manometer are open, we do not include atmospheric pressure in our formula. We only include atmospheric pressure if only one side is open, because in this case they cancel out each other. So in this question we have two liquids. We have oil, then we have water. So oil has occupied this height, xy, then we have water going all the way to the other side. But looking at the question, you can clearly see the highlight of the two levels that are the same. So this is why we can call this P, okay? So the pressure at Y is equal to the pressure at P. So pressure at Y is equal to the pressure at P. This means that the pressure that is the amount, or rather the liquid that is above Y is the one that is creating pressure at Y. Above Y, we have the oil. So we have pressure due to the height of the oil. So height of the oil times the density of the oil times the gravitational force. Now we are not going to add atmospheric pressure because it is also acting on the other side, and if you put them both in the equation, they will cancel out. So this will be equal to pressure at P. Above P we have water. So we have the height of water, the density of water, and the gravitational force. Now we have been provided with the density of water, the density of oil, the gravitational force, and we are required to determine the height xy, which is the height of the oil. So we will be looking for height of the oil. So since we don't have the height of the oil, we will use the letter times the density of oil, which is 600, times the gravitational force, which is 10, and this will be equal to height of water, which is 6 centimeters. Now remember, we can't work with centimeters. So this 7 centimeters here is not relevant because we are only considering the height above P, which is 6 centimeters. So to convert centimeters to meters, we have to divide by 100. We multiply by 1000, which is the density of water. Then we multiply by 10, which is the gravitational force. So here we will have height of oil times 600 times 0 times 10 is 6000, which is equal to, if we cancel out the two zeros, we will have 6 times 10 times 10, which is 600. So dividing both sides by 6000, we are dividing so that we can be left with height of the oil on one side. The height of the oil will be equal to, so these two will cancel, by 6,1 by 610. So 1 over 10 is the same as 0.1 meters. So the height xy is going to be equal to 0.1 meters. If we need to convert this back into centimeters, then we multiply by 100, and this will be equal to 10 centimeters. So now we are going to do just one more example on, on a manometer that has both sides open, and after that, I know we will have understood this concept. Okay, so now in this question, we have 3 liquids in the YouTube manometer. We have mercury at the bottom, and on one side of the YouTube, we have kerosene, and on the other side, we have water. Kerosene has rose to a height of 5 centimeters, and water has rose to a height of 4 centimeters. We have been given the density of water as 1000 kilogram per meter cube. We have the gravitational force, and now we are going to determine the density of kerosene. Okay, we are going to use the setup to determine the density of kerosene. Now in this scenario, we don't have that line that highlights the two levels that have the same amount of pressure. But when you look at the question, you realize that mercury has rose to the same height in either sides. So we have these, so we can create the level for ourselves. So if we call these A and these B, then pressure at A will be equal to pressure at B. Okay? Pressure at A will be equal to pressure at B. Now remember that if both sides of the YouTube are open, we do not include atmospheric pressure in our calculation. So above A, we have water. So the pressure at A is as a result of the pressure due to the height of water, which is given by height of water times the density of water times the gravitational force, and this is equal to pressure at B, which is as a result of the pressure due to the height of kerosene. So the pressure due to the height of kerosene will still be given by the height of kerosene, density of kerosene times the gravitational force. So now we can substitute the values that we have. The height of water is 4 centimeters. So again, we convert that to meters by dividing by 100 times the density of water, which is 1000, times the gravitational force, which is 10. Now this is equal to the height of kerosene, which is 5 centimeters. We convert that to meters by dividing by 100 times the density of kerosene. We don't know it. In fact, that is what we are looking for. So we have it here as the density of kerosene, then times 10. So if we work this out, we have 4 times 10 times 10, so that is 400, which is equal to 0.5 times the density of kerosene. Now to obtain the density of kerosene, we will divide by 0.5 divide by 0.5. So this cancels out, then 400 divided by 0.5 will be equal to 800 kilogram per meters cubed. And that is the density of kerosene. So now you've seen that you can use a YouTube manometer to actually determine the density of a liquid. Now I need you to pay attention to this. Mercury rose to the same level, okay? And then on this side we have kerosene, on this side we have water. The pressure at A is equal to the pressure at B. But how come kerosene has a higher height than water? So kerosene has a higher height than water because it has a less density than that of water. So the bigger or the greater the density of a liquid, the less the height, okay? So kerosene, which has less density, has a greater height than water, which has more density. So in a scenario where you are given a diagram like this with two different liquids, and then you are asked which liquid has a greater density, then it will be the liquid with a smaller height. The greater the density, the less the height, okay? So now we are going to highlight the different types of barometers that we have that are used to measure pressure. We highlighted at the beginning of the topic that the instrument that is used to measure pressure is called a barometer. So a barometer contains mercury, and it is used to determine the value of pressure. Now we have 4 different types of barometers. The first one is a simple mercury barometer, and this is how it looks like. It's that simple. So you have mercury put in a basin, and then we have a long tube that has mercury in it. And what happens is that this mercury barometer is placed in an open field where atmospheric pressure is acting on the mercury, and the pressure makes the mercury to be pushed and move up the tube. Okay, so like you can see, this is an open space. So atmospheric pressure acts on this and pushes the mercury downwards, and for it to escape, it has to escape through the tube. So it rises to a certain height, and when it rises to a certain height, then we are able to determine the atmospheric pressure of that region. Now remember, when we were talking about the units of pressure, we said that we will discuss what does millimeters of mercury mean, what does centimeters of mercury mean. So if you place this barometer outside here and the mercury rises to a height of, let's say, 70 centimeters, then we can say that the pressure in that region is equal to 70 centimeters of mercury. And if you convert centimeters to millimeters, that will be 70 times 10, which will be 700 millimeters of mercury. Now let me repeat. If you put this barometer outside here, the atmospheric pressure outside in this region is going to push the mercury downwards, and the mercury is going to go up the tube, and then it will rise to a particular height. If that height, for instance, is 70 centimeters, then we can say that the pressure in that region is equal to 70 centimeters of mercury. If you need to convert that to millimeters of mercury, then you change the 70 centimeters to millimeters to get 700 millimeters of mercury. When this mercury barometer is placed at the coastal region, it rises to a height of 76 centimeters. So 76 centimeters of mercury is considered to be the standard atmospheric pressure. Because remember, the coastal region is at the lowest point. It's at sea level. So 76 centimeters of mercury is regarded to be the standard atmospheric pressure. Now, if we wanted to convert this into pascals, what would we do? So we know that pressure is equal to height times density times G. So the height of mercury is 76 centimeters. So we divide by 100 to convert that to meters, times the density of mercury, which is 13,600, times the value of G, which is 10. If you multiply that, you will obtain 103,360 pascals. So this is said to be the standard atmospheric pressure, which is also known as 1 atmosphere. Remember, the other unit for measuring pressure is atmosphere. So 1 atmosphere is equivalent to an atmospheric pressure of 103,360. So just by talking about a simple mercury barometer, we have learned how to express pressure in terms of centimeters of mercury, millimeters of mercury, and now convert that into pascals or into Newton per meter squared. Now the other type of barometer is a 14 barometer, which was discovered by someone called 14. So it is an improvement of the mercury barometer. So if you use the 14 barometer, you are able to get more accurate results. The analog barometer is used in stations. It is not very, it is not portable, okay? It is not a portable barometer. It is used in places where atmospheric pressure is measured, like in weather stations and all. Then we have the pressure gauges, which are used to determine the pressure of gases. And these are the ones that are used in garages and even in petrol stations. So make sure that you remember how to convert from centimeters of mercury, millimeters of mercury to pascals, because that is a very common question. Now I'm going to give you a few questions that you're going to use to test whether you have understood the contents of this lesson. Now learners, for your practice, you will attempt these two questions. Explain why there is a big difference between heights of water and mercury column that can be supported by atmospheric pressure. Then number 2, we have a diagram here. We have two liquids, X and Y. The heights of the two liquids have been given based on the level that has the same amount of pressure. We have the density of liquid Y, and we have the gravitational force. With that information, determine the density of liquid X. So thank you so much for being in this lesson. See you in the next lesson.